Okay, so there's a couple problems with small samples. One we've already looked at, and that is that the standard error, the smaller the sample, the larger the standard error is going to be, and that's going to create issues when you go to do your hypothesis testing. The other problem is, remember in the central limit theorem, we said that as long as a sample is large enough, the sampling distribution will approach the normal distribution. The population mean will be the mean of the sampling distribution. The standard error is the population standard deviation divided by the square root of n. We have all these really neat things happening. Unfortunately, we had that little condition when the sample's big enough. So what does that really mean for us? Well, if the sample's big enough, we can use the standard normal distribution, which is this magenta line here that you see. Unfortunately, the reality is most of the time our samples are not big enough. Certainly they're not tending towards infinity. And so we have to use another distribution, actually a family of distributions called the T-distributions. So the deal with these T-distributions is they're very similar to the normal distribution. You can see a few of them here. The purple, the green, and the blue are all different T-distributions. This DF stands for degrees of freedom. In the test that we're using, it'll be 1 or 2 less than what the actual sample size is. So this might be a sample size of 2, of 10, of 26. You can see the closer, or the higher that our sample size gets, the closer that our student's T-distribution gets to the normal distribution. And eventually, as we go to infinity, in other words, as we get larger and larger sample size, we basically get the standard normal distribution. Now, this is one of the reasons why a sample size of 25 or 30 tends to be the minimum recommended sample size, because once you get that high, your T-distribution and your standard normal are pretty similar. So what does this actually mean for our calculations? Well, let's take a look at that. So on the left here, you see the confidence intervals that were created with your samples of size 5 using the standard normal. And when I say using the standard normal, remember that we subtracted 1.96, or you subtracted 2 standard errors from your mean, added 2 standard errors to your mean, and that gave you your 95% confidence interval. Now that would be just peachy if our sample size had been large enough. If we had had, say, 25, 30 movies in our sample. But we didn't, right? We had a smaller sample. We had 5 movies in each sample. So that's going to give us a degrees of freedom of 4. And if we were to calculate really the number of standard errors that we should have gone in each direction, it would actually be closer to 3 because of our small sample size. Now what that would do is it would increase our confidence intervals. You can compare them side by side, right? Look at Stacy's here. Her 95% confidence interval using the standard normal went from a little above 90 to a little above 130. When we actually use the T-distribution, which is technically the correct one to use here, her confidence interval now goes from a little above 80 to almost 140. And you can see that stretched effect. Notice that the axes are the same, so I'm not creating an effect by increasing the units here on the axes. In fact, some of these, Ashley's, Jing, and Joseph's went, well, I guess Ashley and Joseph's went off the chart here, were even above 180. Now, one thing you'll quickly notice is, remember that the population mean is 119, correct? Well, if we look at what happens when we use the T-distribution, Stacy caught it, Ryan caught it, Amanda did not catch it, all of the others caught it. And again, this is nothing to do with Amanda's sampling. This is to do with randomness. This is why we don't always catch the population mean with our confidence intervals. But here's the one to focus on, Ryan. Over here, Ryan did not catch the population mean with his confidence interval. And here he did, because his confidence interval had expanded to go up above 120 here. So let's take a look at how we would use sheets to adjust for this t-distribution instead of the standard normal. So let's say I'm going to create a 95% confidence interval using the actual population data. So again, I do know that the mean is 119 minutes. I can calculate the standard deviation of my 100 movies on the times list, and then divide that by square root of 5 to get the actual standard error, not the estimated one that you were able to produce with your sampling of 5 movies each. So the first thing I want to do is the lower end, oops, not a formula there, the lower end of my 95% confidence interval. So just like you had done before, we'll do a formula. We'll start off with the mean, and we'll subtract a certain number of standard errors. So let me go ahead and multiply this by the standard error. Now let me come back and figure out how many standard errors am I going to go below the mean. Well, here's where we had put in 2 or 1.96, maybe if you were more precise. But remember, that's using the standard normal. That's assuming that we have a sample size that's large enough. We know now that we don't. We know now that our sample size of 5 means we really need to use the t-distribution instead of the standard normal. So how do we do that? So here's this. I'm going to type this in and I'm going to talk about it. So the t dot inverse dot 2t, and what that is, the t stands for the t-test, of course. INV means I'm going to give the sheets, I'm going to give it the alpha level that I want, the risk of type 1 error that I'm willing to take. In other words, 1 minus the confidence that I would have. So 95% is my confidence level, which means 5% is the percentage of the time that I'm willing to take a type 1 error. So my probability here would be 0.05. And then it's going to give me a critical value. It's going to give me the number of standard errors I need to go away from the mean. The 2t here stands for the two-tail because I don't know, I want to create it in both directions, the confidence interval around the mean. And we'll talk a little bit more about that when we look at the p-values. But anyway, I'm getting this t inverse two-tail. Probability is 0.05. That's my alpha level. My degrees of freedom is 4. So this is 1 less than my sample size. And we'll talk more about that also. I don't want to get too much into the degrees of freedom, but it's basically saying how close am I getting to that standard normal. Now if I highlight this, it'll actually give me an interim calculation. Okay, so you can see there that that's 2.77. In other words, with this sample size of 5 movies, I should actually be going 2.77 standard deviations below and above the mean to create the correct confidence interval. So I'm going to go ahead and press enter there. And the 95% the upper end of my 95% confidence interval will be very similar. Again, I'll start off with the mean. I'll add, it's going to end up being the same number, but let me show you again how I did that. So t distribution, I'm using the inverse. The inverse again is just I give it the alpha level, it gives me the number of standard errors that I need to go away from the mean. And my alpha level is 0.05, 5% risk of error, 95% confidence. Degrees of freedom again is 4. And that's the number of standard errors. So I'm going to multiply that 2.77 by the number of by the standard error. So this is going to give me a confidence interval 75, 76 to 163. So what this is saying, 95% of the time, if you take 5 movies from this list, calculate the length, and get the average, 95% of the time, that average is going to be somewhere between 76 minutes and 163 minutes. Now what we can also say is looking backwards, if we get a movie, or sorry, get a sample of 5 movies, calculate the mean, use our estimated standard error to create a confidence interval around it, roughly 95% of the time we'll catch this population mean. So if you can see what's going on here, there's a back and forth. We can either start with the actual population mean, create a confidence interval around it, and then see whether or not we're in the confidence interval. Or we can start with our sample and create a confidence interval around our sample, and that gives us a sense of whether the population mean is inside of our confidence interval.